Welcome back, students. Let's discuss some more nuclear reactions. And in this reaction, if this americium is used as target nucleus, while this is bombarding nuclei, helium are normally in nuclear reaction. We call it alpha ray. So whenever americium is bombarded by alpha ray, what happens? This alpha ray gets enter into the nucleus of americium, or it is absorbed by americium, and definitely a heavier nuclei is produced. So the heavier nuclei is berkelium, and along with three neutrons. So now if you balance the equation, 95 plus 2 is equal to 97, and here we have 97 plus 0 is equal to 97. 242 plus 4 is equal to 246. 243 plus 3 neutrons, so we have to add 3 here, so 246 there, which makes the equation completely balanced. Now this reaction can be used for the production or synthesis of heavier nuclei, that is berkelium. Then curium, when it is targeted or it is bombarded by carbon 12, so what happens, this carbon also gets inside the nucleus of curium, it is absorbed, and a heavier nuclei of nobelium 102 is produced. Now again, 96 plus 6 is equal to 102, and 246 plus 12, you can count it. So 4 neutrons are produced during this reaction, and a heavier nuclei of nobelium is formed. Now how we have to bombard these particles which are comparatively heavier than neutron or beta particle or gamma radiation. So in order to get the required acceleration or required speed, required kinetic energy of these particles, we have to use a particular device which is called in nuclear chemistry as accelerator, and this accelerator is used to increase the kinetic energy of bombarded particle on target nuclei. There are different types of accelerators, and one type of those accelerator has been given here, that is cyclotron. So in cyclotron, these radiations gets enough, or they attain enough kinetic energy, sufficient amount of kinetic energy, which is required for initiation of these nuclear reactions, and these heavier nuclei are synthesized in the lab. So this is one of the synthetic method used for synthesis of heavier nuclei than the uranium and so on. Now, californium is when bombarded by boron 11, so lawrencium 103 has been produced along with 4 neutrons, and once again you can balance the nuclear reactions. While dealing with nuclear reactions, we will come across certain particles which are used for bombardment, or certain phenomena which can be observed during a particular nuclear reaction. Either we have to bombard lighter nuclei, comparatively lighter nuclei by neutron. Either we have to get or bombard the nuclei by gamma ray, but bombardment in the case of gamma ray is quite less, while this gamma ray is normally produced during the nuclear reactions. Either negatron is produced during a nuclear reaction, or positrons are produced, or another process which takes place during a nuclear reaction is electron capture. So these process or production of these particles, generally we have to modify or to adjust the neutron to proton ratio of a nucleus. Sometimes we will have less number of neutron than required, and sometimes we will have more number of neutron in the nucleus than it requires. Therefore, in case of maximum or more number of neutron, nuclei will try to get rid of excess of neutron, and in case of less number of neutron, the nuclei will try to attain more neutrons in order to attain the required stability. So attaining of neutron can be carried out by several steps, and similarly reduction of number of neutron in the nucleus can be carried out by various steps. For example, this is a neutron, which, let's suppose this is a nucleus where neutrons are in excess. So what the nucleus will do, nucleus will convert one neutron into a positron and negatron. So positron, actually this is proton and electron. So what happens, one neutron will disappear and a pair will be produced, a pair of two charged particles, proton and electron. So whenever we are talking about proton and electron, so we also should know that where is the space of electron in the atom, and where is the actual location or position of proton in the atom. So proton resides in the nucleus, it exists in the nucleus, while electron will be moved toward shells outside the nucleus, and at the expense of disappearance of one neutron, what nucleus will get a proton, and it will reduce the neutron to proton ratio by a considerable number. And if this one reaction or one step is not enough, another neutron will also be converted into proton and electron, and so on and so forth, until and unless the required ratio of neutron to proton is availed by the nucleus. This is an example of indium. And also we have discussed certain other reactions where beta or negatron has been produced. So in this case, the lighter nuclei is converted into heavier nuclei at the expense of beta ray emission. So this is now sensitive toward beta ray emission, and upon beta ray emission 10116 is produced. In this case, if you think that what happens, so when beta radiation, this beta radiation is actually that electron. So electron is emitted, or it is uh, it is away from the system or from the atom, and what happens, one proton in the nucleus of the atom increases because atomic number is completely the number of proton inside the nucleus or electrons in the shell. But here we are not concerned with electrons, but we are concerned with proton in the nucleus, and one proton is increased, which makes or which changes the nature of the atom from indium to tin. Another one, this proton is when in excess. So now in this case we have to consider neutron to proton ratio. So neutron to proton ratio, if it is less than 1, so less than 1 means number of proton are more than number of neutrons. So what the nucleus will do, now the nucleus will convert its proton into a neutron and a positron. So positron will move away from the nucleus and neutron will reside there, and the ratio of neutron to proton will accordingly increase. And this is a reaction where the antimony is converted into tin, which is a heavier nuclei, and a lighter is produced by disappearance of a proton in this reaction, and with the emission of a positron during this reaction. Now, whenever neutrons are less, so in this case neutron has been produced or added to the nucleus. In this case neutron has been removed from the nucleus, and in case when the number of neutron is less, then the nuclei will also adopt another strategy, and that strategy is actually pair production, pair annihilation. And this, in this pair annihilation, one proton and electron, or this is called actually electron capture. So the nuclei will capture an electron from outer shells, electron will combine with a proton, the pair will disappear, and a neutron will produced in the nuclei. So this is also another possibility for a nucleus in order to adjust its neutron to proton ratio. So these are some representative nuclear reactions in your course. Now you can try some more reactions depending upon your efforts and your needs. So this was all about nuclear chemistry of next, and almost the last portion of this chapter is comparison of lanthanides and actinides. Let's compare them. So while we are comparing two or more than two things, we have to look for similarities and then for differences, that what are similar points or identical points in these two series, and what are differences in these two series. So the one common point in both the series lanthanides and actinides was their oxidation state, which was 3 common for both lanthanides and actinides. Both the series are F block because F orbitals subshells are successively filled, or by definition we can say that last electron enters into anti-penultimate subshell. Therefore, both of them were called F block elements, so they belong to the same family on the basis of anti-penultimate subshell. Contraction phenomena in both the series was observed, and it was almost the same, that ionic and atomic radii was observed to decrease toward right upon increase in atomic number, and absorption spectra or color of both the species was due to both the series was due to FF transition, where F orbital undergoes splitting uh, depending upon the environment of the ion in its solution or ion in its compound. So the color was actually imparted because of electronic excitation between two or more than two F levels at ordinary temperature in the range of UV visible spectra. So color of complexes or phenomena of color of complexes was same for both the series. If you look at magnetic properties of both the series, so magnetic properties, most of them were paramagnetic, and paramagnetic behavior of the lanthanides and actinides was because of the unpaired electrons in F subshell. So both the series and most of the members of the series possess unpaired electrons in their F subshell, and on the basis of these unpaired electron, they were paramagnetic in nature. And this paramagnetism, it was not simple magnetism which could be explained by the simple formula of spin or number or spin of unpaired electrons. Rather, another formula which was a bit advanced was used, where orbital contribution was also considered. And the orbital contribution, although this is a difference between the two species, the orbital contribution was quenched in case of actinides, while it was more in case of lanthanides. So magnetic properties in case of isoelectronic system of lanthanides and actinides, when they were observed experimentally, so the magnetic properties were more for lanthanides and less for actinides.